title of this next talk sums it up better than anything I could actually say. He's here to discuss how data is changing life, the universe, and everything. Please welcome on stage theoretical cosmologist Roberto Trotta.
When is the last time you looked up at the sky and experienced a sense of awe? And if you have you seen the Milky Way? Who has seen the Milky Way on the sky here? Hands up. Who's seen the Milky Way? With their own eyes? Not many folks, actually. And if you have to ask whether you've seen it, then you haven't. Because the sky, like this, we don't get to see it anymore. We've lost our primal ancestral connection with the sky because we live in cities that are polluted by heavy light pollution, and therefore we can't look up at the night sky and wonder what's out there anymore. But modern science and technology bring us back that sense of wonder and awe multiplied 1,000 times. Here's a picture of the sky. I want you to get a sense of proportion by looking at the moon to scale in this picture. But I want you to focus on the little yellow square, which is a patch of the sky as small as to fit inside the eye of a needle held at arm's length. It's a tiny patch of the sky that doesn't look anything special, except if you look at it using our most powerful eyes on the universe, the Hubble Space Telescope. This is what you see. There are 5,500 galaxies inside that eye of the needle, and each one of them contains hundreds of billions of stars like the sun. So you do the math, 5,500 galaxies in an eye of the needle multiplied by the area of the sky, 50 billion galaxies in the visible universe. And modern investigations of this kind of big data trove from cosmology have revealed a picture of the universe that's hard to fathom. We've been able to look back all the way to the history of the universe, almost to the very beginning, 13.7 billion years ago, at the primordial moment called the Big Bang, when the universe started in a very highly energetic, very dense state, and then it expanded exponentially for 10 to the minus 32 seconds. At that point, the universe was filled with plasma, like the sun, pretty much, and therefore it was opaque to light. Light could not propagate in the early universe. The universe was full of light that could scatter off hydrogen atoms. But as the universe grew, it cooled down. And as it cooled down, hydrogen could finally form, and the light could escape. So 380,000 years after the Big Bang, the universe, for the first time, became dark. At that point in time, there were no stars, no galaxies, no planets, no heavy elements in the universe, only darkness for the first 500 billion years. And then stars began to form, galaxies began to form, and the dark matter-dominated expansion of the universe continued. As the universe expanded, it slowed down in its expansion. But 6 billion years ago, something truly remarkable happened to the universe. The expansion of the universe was taken over by something we call dark energy, a powerful force that's making the universe accelerate outwards in its expansion and becoming ever bigger, ever faster with time. We've been able to measure a number of things about the universe. We have been able to know with high precision that the universe is 13,796,000,000 years old, give or take 20 million years, which is nothing if you think about it. We don't know the age of the Earth to that kind of precision, and yet we sit on it. And looking back almost at the very beginning of time, this is a picture of the universe 380,000 years after the Big Bang. This is one of the data trove that enable us to understand the composition and the makeup of the universe. What we've discovered is not that those galaxies that we saw in that picture are extraordinary. What's most extraordinary is that pretty much everything that was on that picture is only a tiny little bit of everything there is. There is a dark side to the universe, and we're only beginning to reveal it. So I hate to break you the news if you haven't heard, everything that's out there, those billions and billions of galaxies, are only 5% of everything there is. 95% of the universe is dark, unknown, mysterious, 25% in the form of dark matter, probably a new type of particle beyond the standard model of particle physics, and 70% dark energy, probably a property of the vacuum of space itself that's making the universe accelerate forward in time. Why is it interesting? Why is it relevant? Why do we spend time and effort investigating those things? Well, literally, because the destiny of the universe depends on those quantities. The universe began with a Big Bang, as I said, and in time, which goes from bottom to top in this slide, expands, and it will slow down in its expansion and eventually recollapse into a big crunch if there is enough matter to make it stop and then recollapse. Or, if the matter content is not quite enough, the universe will continue expanding forever at an ever-decelerating rate and just become bigger, but more slowly over time. However, if we have dark energy, which we do, 70% of the universe today is made of dark energy, that expansion will not slow down. The expansion of the universe will accelerate over time, and the universe will become bigger over time at a faster and faster rate, which we think is exactly what's happening to our universe. So if you're asking the question, what is the ultimate destiny of the universe? This is what modern cosmology tells us. The destiny of the universe is an ever-accelerating expansion that in 200 billion years will transform the universe in a very dark, cold, and desolate place where all the matter will have been sucked up in black holes, and the universe will be at a very, very cold state, dominated by dark energy. How do we know all of this? How have we learned all of these incredible discoveries about the universe? Well, if your idea of astronomy and cosmology is this, then this is no longer how it's done. This is the history of astronomy. A lone guy, in this case is Edwin Hubble, looking through his big telescope, discovering new things. In this case, he discovered the number of galaxies that at that time weren't known to be galaxies, and he established the expansion of the universe. That was in 1929. Today, this is what cosmology looks like. We use billion-dollar instruments that are often spaceborne, worldwide collaboration of thousands of engineers, scientists, and computer scientists to generate a great amount of data about the universe. And those data, in order to be understood, interpreted, and massaged into knowledge about the universe, what they require is computer power, sophisticated algorithms to disentangle the faint signals we're looking for from the big noise that's out there. And that can only happen nowadays with big data techniques, artificial intelligence, machine learning, statistically sophisticated tools to disentangle those nuggets of knowledge from the big data that we are getting in cosmology. So what do I mean by big data in cosmology? I want to give you a sense for how the state of play has evolved over time. And so here's a little movie that I put together with my students at Imperial what our ambition is and was to create a map of the universe that will encapsulate the entirety of human knowledge over time to enable us to chart how our understanding and knowledge about the universe has evolved over time. So in this movie, I hope you can see it. It's not very sharp, but the x and y axis on the plane are the two angles on the sky where objects are, and on the vertical axis, it's distance from us. So each one of the horizontal line is 1,000 times further out than the previous one. And this is now 1800. There isn't much to see on that plot. I'm not showing all the data for clarity, but the point is that for many, many hundreds of years, despite the inventions of the telescope in the 1600s, we didn't learn much about the universe. If I now make time go forward, you will see that little by little, we start populating this by new objects, new discoveries. So we've got the Earth orbit at the bottom, the solar system is in between, the galaxy, the stars in our galaxy are in yellow, and at the top, the cosmologically distant galaxies elsewhere in the universe. And you can see that until the 50s, not much happens. The asteroid belt appears in gray. There's a few galaxies being discovered, but watch what happens from the 1990s onwards. Now, the growth of data is exponential, and we've been able to fill out all of this gap in knowledge by means of CCD cameras, which were the real game changer in the late 80s and 90s, robotic telescopes, and the data processing capabilities that are afforded today by cheap and fast computer power to our disposal. So where does that leave us in terms of our place in the universe, the pale blue dot that we are lucky to sit on in Carl Sagan's memorable words? Where are we in the universe? What do we know about our place in the universe? And what do we know about the existence of life elsewhere in the universe, now that we've charted out such incredible length of distances in space and time? Well, we've looked everywhere in the solar system. We looked to our nearest neighbor, Mars. We've gone to Mars with rovers. We've explored it. And you can see Mars is a pretty desolate place, despite the fact that it is the planet that's the most similar to us in the solar system. It is not a planet that harbors life. It might have in the past. There's evidence for liquid water on Mars billions of years ago. There is solid water in the form of ice on Mars today, but the hopes for life on Mars are pretty slim. So we need to look elsewhere, further afield in the universe. We've explored all of the other planets in the solar system with robotic means, and we haven't found life. We have found conditions that are interesting and perhaps potentially suitable on some of the moons of Saturn, for example, but no life. So we need to look further afield. But fortunately, we now know that the Sun is but one of 300 billion stars in our galaxy, and there is plenty of other places where life could have emerged in the universe. So to give you a sense, here is our map of the universe. At Imperial, we've set this up in a global data observatory at the Data Science Institute, so you're immersed in the data. I couldn't quite reproduce it here, so I'll just give you the two-dimensional version instead. So in this map, on the horizontal axis is a position in the sky of objects, and on the vertical axis is the distance from us from Earth. And again, it's a logarithmic scale, meaning that each one of the ticks is 10 times further away than the previous tick. So down here, we got low Earth orbit satellites in red. You can see the horizontal line, which is geostationary satellites, 36,000 kilometers up. Then you see the various planets on the solar system, which are the gray circles, and the Sun in yellow. The big band, the big green band, is the asteroid belt between Mars and Jupiter. But I want you to focus on this up here. Up there, if you squint, you'll see Voyager 1. That is the farthest man-made object in the universe, a probe that was launched 40 years ago and only now is getting lost into interstellar space at the edges of the solar system. It's traveling at 15 kilometers per second, and that sounds fast, but it's a snail's pace in cosmological terms. Because where next? If you want to cross that interstellar space, this is where we need to go. We need to cross all of that big expanse of nothingness until we get here, to a dot that you can't quite see. That's Proxima Centauri, our nearest neighbor star, which does harbor a planet, which, however, probably does not have the conditions for life. How long would it take for Voyager 1 to get there at current speed? Remember, this is the best we've achieved so far. 27,000 years. So this ain't going to happen anytime soon, obviously. And if we want to look for life elsewhere in the universe, we need to go further afield. We need to go to the galaxy, which is the yellow band there. Each one of the dots is a star, but focus on the purple dots. The purple dots are exoplanets. Those are planets that go around other stars in our galaxy, and we've discovered over 3,000 of them to date. And further afield, if you go another 6 orders of magnitude up, we get into cosmology. Each one of the green dots now is an entire galaxy. And there will be plenty of planets there, albeit beyond our means of discovery at present and in the foreseeable future. This is the evolution of the number of known exoplanets over time. You can see it's an exponential growth from 1995, when the first exoplanet was discovered, until today. Nowadays, we discover hundreds of exoplanets in a day, and as of last week, we have discovered an exomoon, a moon orbiting a planet orbiting another star. So that's extraordinary. This is taking us into new territory, because what we've discovered is that all of these planets are actually quite different, quite peculiar, not at all what we had expected. And this is a big data game now, because everything is coming at us in big numbers. There are 10 to the 80 atoms in the visible universe. That seems a large number. It is a large number. It does pale in comparison with the number of possible tweets, 10 to the 396, especially now that we have 280 characters to do them. The difference is that most tweets are gibberish and meaningless, let's face it, while we have very sophisticated models for where those galaxies are in the universe, or where those stars are in the universe, and we can use our knowledge of physics to understand those data in a way that would otherwise not be possible. And by doing that, we've been able to map out thousands of planets, and we discovered that those planets are very different. Big planets, small planets, going around stars of very different kind to the Sun. So perhaps life elsewhere in the universe will live in very different conditions than we are used here on Earth. Kepler-16b, for example, is a planet that orbits a binary star. And we would not have thought it possible scientifically, well, except, if you had watched the right kind of movies, perhaps you would. But this is a case where science is catching up with science fiction. And really, we are now coming to a point where we're understanding that our blueprint for the solar system is not the only one in the universe. Here is a diagram showing on the horizontal axis the distance from the star, and on the vertical axis the size of the planets that we've discovered. The kind of Earth-2 planets that we're looking for are here, where the Earth is. You see there are not many dots there, meaning our technology is not quite advanced enough to see them. It's easier to see big planets and planets that are closer to the star. But actually, if the star is very different from the Sun, it might be that all of those very, very strange planets going around perhaps in 10 days around the star, not at 365 days, will harbor the conditions that are right for life. Very different life than what we have here on Earth, but nevertheless, life. And so then, the question is, as Fermi famously posed it many years ago, where is everybody? If we are convinced, thanks to these sophisticated new discoveries, that planets are everywhere in the universe, why haven't we heard from anybody? So let's do the maths. 300 billion stars in the galaxy, in the Milky Way, 15 billion galaxies in the visible universe, about 7,500 billion potential planetary systems in the visible universe. That's an enormous number. And even if we restrict our attention to what we believe is the number of planets that could potentially harbor life, where the conditions are right, we still get 200 billion habitable planets. So it's a numbers game. The question is not whether life is out there. The question is, where is it? And the other question is, does it last long enough? Because if you think about it, in order for life to make itself known to others via, say, radio waves, it takes time for those radio waves to travel through the universe. We've only been transmitting for about 100 years. So those radio waves have now reached about 15,000 stars around us. If somebody's on that star, picking up that signal, they send back a message to us. It will take another 100 years to get to us. Who knows whether we will still be around to answer then, by the way things are going on our planet. And so the fact that we have not heard from any other advanced civilization might mean, statistically, probabilistically, that advanced civilizations get wiped out quite quickly after they reach the means of being able to transmit signals, and then they just go in a blink of a cosmological eye, which would spell disaster for ourselves, and sort of a call to arms in terms of the stewardship of our own environment, of the Earth, and taking good care of our pale blue dot. So in the future, then, we're going to investigate things even more thoroughly, and that's where data science comes in. The Large Synoptic Survey Telescope will generate an enormous amount of data. We'll take 200,000 images of the sky per year. Nobody can ever inspect visually those data. We rely on machine learning AI systems to tell us what's interesting and dive deep into it with statistical means. The Square Kilometre Array Radio Telescope is a continental-size array of telescopes that will generate 5 times the internet traffic of 2015 per year, and will require a huge amount of computing power just to analyze those data. So we're really coming to a point where our progress in our knowledge about the fundamental reality of the universe is no longer stopped by the number of data points that we have, but by our ingenuity and capabilities of statistically and mathematically process this data and make sense of them in a very challenging fashion. I want to conclude by asking perhaps the biggest question of them all: why? Why should we be spending time, energy, capabilities, and most importantly, why should we be spending the energy of bright young minds, young women and men, looking for dark matter, looking for life elsewhere in the universe, when we have arguably more pressing problems here on Earth to worry about? Well, there are many reasons. I want to give you one compelling reason today, and it's a lesson from history. If you look back at the late 19th century, when Michael Faraday at the Royal Institution in London was investigating electricity and magnetism in his lab, the Chancellor of the Exchequer visited him and asked, "Dr. Faraday, what is the point of this electricity of yours?" And Faraday famously answered, "One day, sir, you may tax it." And indeed, we do tax it, and electricity and magnetism are at the core, at the heart of everything our society is about. We wouldn't be here without them. When Albert Einstein in 1915 invented general relativity, he had no inkling that 100 years later, every time you look yourself up on a map, the GPS signal in your phone gets corrected because of general relativistic effects of time dilation between the GPS satellites 36,000 kilometers up and the Earth. Without the general relativistic equations that your phone implements in order to geolocate you on the map, your GPS would be off 10 kilometers a day. So every time you look yourself up on a map, spare a thought for good old Albert. When Stephen Hawking in 1974 postulated that black holes are not totally black, that they actually evaporate, emitting a kind of radiation, he had no idea that in the 90s, 20 years later, an engineer named John Sullivan, while working on a radio telescope to detect these signals, he would invent an algorithm to disentangle radio signals from evaporating black holes that is now in pretty much every Wi-Fi device and it's now used by billions of people worldwide. So it's clear that this path of innovation and technology development has come serendipitously to us, and that's why we need to continue investing our effort, energies, and time doing just that. So when we produce this kind of dark matter simulations, pushing the boundaries of what's possible from a computational point of view, pushing the boundaries of what's possible from an engineering point of view, pushing the boundaries of what is possible by worldwide collaboration of scientists and engineers, what we're doing is looking for dark matter because we think it matters, because we think dark matter is one of the fundamental building blocks of the universe, and this is curiosity-driven research. But what I can confidently predict is that while we don't know what technological advancements dark matter will bring us in 20, 100 years' time, I can confidently predict that those advances will change the way that our society works, just like they always have in the past. So we've come a long way. We've gone from a picture of the universe where the Earth was at the center of the universe, and all of the planets went around it. This is the Ptolemaic model of the solar system. We felt special. We felt in a special place in the universe. And that has been dethroned hundreds of years later by Galileo and Copernicus, who said that the sun is at the center of the solar system. We're just one of the planets. Well, even that picture isn't general enough, because now we know that we are not special. Our solar system is just one among many very pervasive systems in the galaxy, and indeed, as of today, we can routinely detect planets going around other stars but the sun, and this is a great achievement of technology, it's a great achievement of fundamental science, it's a great achievement of data science. We wouldn't be able to do any of that without computational means that are sometimes surpassing what is commercially available and possible by tackling problems that are sometimes beyond the edge of feasibility, and we need to invent those systems because they simply do not exist. And so, in going forward, what we know is that the data avalanche will continue, and we will map out all of the visible universe in our lifetimes. At that point, it won't be data that's holding us back. It won't be physics that's holding us back. It will be data science. It will be our ingenuity to decrypt those data and understand how they work together in a way that makes sense with our physical theories. And that is a goal that we can only achieve by using advanced AI systems, machine learning, principal statistics, and computer science. So I can confidently say that the best discoveries still lie ahead of us. Thank you.